Have you ever stared at the night sky, feeling the vastness of the universe stretching out above you, and wondered if it's all real, if what you see, feel, and experience is truly the fundamental reality, or just an illusion? This question has haunted humanity for centuries. Philosophers, poets, and scientists alike have all wrestled with the nature of existence. Today, this age-old mystery has taken a digital twist. Are we living in a computer simulation, crafted by some advanced intelligence? The Matrix made this idea famous, turning it into a pop culture phenomenon, but the concept goes far beyond science fiction movies. Some leading thinkers, like philosopher Nick Bostrom, argue that if advanced civilizations can run ancestor simulations, then statistically we're more likely to be simulated than real. It's a theory that sparked intense debate in scientific and philosophical circles. That's a mind-bending thought. Your memories, your triumphs, even your pain, could be nothing more than lines of code, carefully programmed to create the illusion of reality. But how would we ever know? Is there any way to peek behind the curtain and glimpse the true nature of our world? Any test we devise, any experiment we run, could itself be part of the simulation's design, making it nearly impossible to break free from the illusion. Still, physicists and mathematicians search for clues, tiny inconsistencies, unexplained patterns, or fundamental rules that might reveal a cosmic programmer's signature hidden in the code of reality. For a while, quantum mechanics, where particles don't have definite properties until observed, seem to hint at a simulated reality, as if the universe only renders itself when we look. But recent discoveries in mathematics and quantum gravity suggest our universe is far more complex, mysterious, and unpredictable than any program we could imagine or create. The cosmos, it turns out, is stranger and deeper than any simulation, inviting us to keep questioning, keep exploring, and keep searching for the truth. The simulation hypothesis asks a question that feels straight out of science fiction. If we can create virtual worlds with their own rules and inhabitants, why couldn't a more advanced civilization create ours? What if our reality is just one layer in a vast stack of simulations, each more complex than the last? In video games, characters don't know their code. They move, interact, and even make choices, all within the boundaries of their digital universe. They live by rules set by designers, just as our universe might run on programmed laws, written in the language of physics and mathematics. This idea is both thrilling and unsettling. It challenges our sense of reality and makes us wonder about the true nature of existence. Maybe we're part of a grand experiment, or maybe our reality is fragile, just software that could be shut down or altered at any moment. For physicists, though, it's a testable idea. They're searching for evidence that could reveal the digital nature of our universe. If the universe is a program, it should have computational limits, just like any computer system we build. Computers process information in discrete bits, with finite speed and memory. Our universe might have similar constraints, hidden deep within its fabric. So, a simulated universe might reveal itself through pixels of space and time, tiny, indivisible units, like the smallest building blocks of reality. Or perhaps the laws of physics would show shortcuts, optimized for efficiency, just like a programmer would do to save resources and processing power. If we find evidence of these digital fingerprints, patterns, or anomalies that can't be explained by natural processes, it could point to a simulated reality. But if the universe is continuous and infinitely complex, with no signs of digital structure, it might be something else entirely, something beyond our current understanding. The search for these clues is at the heart of modern physics, driving researchers to explore the deepest mysteries of existence. Are we digital dreams, living in a cosmic simulation, or is our reality something more profound? The answer may change everything we know about ourselves and the universe. In video games, only what you see is rendered in detail. The rest is blurry or missing, saving processing power. Some wonder if the universe works the same way. Does reality render only when observed? Quantum mechanics says particles exist in many states until measured, like a game only loading details when you look. Imagine walking through a forest. The tree in front is sharp, distant ones are fuzzy until you approach. This render-on-demand idea suggests reality is interactive, generated in real time. Physicists search for evidence, like the Planck length and Planck time, the smallest possible units of space and time. If space is made of discrete chunks, it would be strong evidence for a digital universe. It would be like zooming in on a photo and finally seeing the pixels. The quest to find these cosmic pixels is one of the deepest in science. Are we seeing the code, or just the canvas? To understand how reality might be rendered, let's look at Anderson localization, a phenomenon where electrons get trapped in disordered materials. This effect is a striking example of how the tiniest changes in a system can have enormous consequences, revealing hidden rules that govern the universe at its most fundamental level. In a perfect crystal, electrons move freely, making it a conductor. The regular, repeating structure acts like a smooth highway, allowing electrons to zip through with almost no resistance, carrying electricity efficiently from one end to the other. Add disorder and electrons get stuck, turning it into an insulator. The once smooth path becomes a chaotic maze, blocking the flow and trapping the electrons in place. This isn't a gradual change, it's a sudden switch, like flipping a light. One moment, the material conducts, the next, it doesn't. There's no in-between. Imagine crossing a stream. If the stones are evenly spaced, you can cross easily. But if the stones are scattered randomly, you might get stuck halfway, unable to reach the other side. The difference is dramatic and immediate. This abrupt transition is called a phase change, like water freezing instantly at a certain temperature. Suddenly, the entire system shifts from one state to another, as if obeying a hidden command. Anderson's insight was that even a little disorder can trigger a dramatic, binary shift in a material's properties. It's as if the universe has a built-in threshold, and once crossed, everything changes at once. This on-off behavior feels digital, like a computer variable flipping from 0 to 1. It's a reminder that nature sometimes acts in discrete steps, not smooth gradients. It's a key piece in the puzzle of how reality might be rendered. These sudden, all-or-nothing changes suggest that the universe could be built on digital-like rules, hidden beneath what we see. If the universe can flip states so sharply, is it following a hidden script? Could there be a deeper logic, a cosmic code, that determines when and how these switches occur? Or is this just the language of physics at work? Are these abrupt changes simply the result of mathematical laws playing out in complex systems? These sudden changes hint at deep mathematical rules beneath the surface. Patterns repeat across scales, from the tiniest atoms to the largest galaxies, suggesting a hidden order. But do they point to a simulation, or something even stranger? The universe's hidden switch remains one of its most intriguing mysteries, inviting us to keep searching for answers. For decades, Anderson localization was accepted, but a full mathematical proof in 3 dimensions was missing. In 2024, mathematicians Hongzhi Yao and Jun Yin finally delivered that proof. They showed there's a sharp threshold. Below it, electrons move freely. Above it, they're trapped. This isn't a gradual shift, it's a binary flip, just like a computer switch. Their work confirmed that nature can be governed by sudden digital-like transitions. It's like proving the exact point water freezes, nature's own on-off switch. This proof doesn't just explain materials, it reveals how the universe can change states with mathematical precision. It's a stunning example of how deep, digital-like rules shape our reality. But does this mean we're in a simulation, or just that the universe is mathematical at its core? The 2024 proof of Anderson localization shows how the universe can flip a switch, just like a computer program. Imagine a game where a character can walk through some walls but not others, based on a simple rule. The universe seems to have similar rules, sharp, absolute transitions dictated by mathematics. This digital-like behavior fueled the simulation hypothesis. Maybe we're seeing the code of the cosmos, but a metaphor isn't proof. Just because nature acts like a program doesn't mean it is one. Our computers follow the laws of physics, so similarities are expected. The Anderson proof shows how math governs reality, but it doesn't reveal a programmer. It's a mechanism, not a motive. To prove a simulation, we'd need a different kind of evidence. The search continues. In late 2025, physicists Mir Faisal and Lawrence Krauss published a bombshell: the universe cannot be a computer simulation. Their argument draws on Gödel's incompleteness theorem, which says any formal system complex enough for arithmetic will have true statements it can't prove. A computer simulation is a closed, algorithmic system, subject to Gödel's limits. If our universe were a simulation, there would be truths about reality that the simulation's code couldn't capture. This creates a paradox. A complete theory of everything would be impossible from inside the simulation. But physics seeks a full, self-contained description of reality. If we can, in principle, describe all physical laws, our universe must be more than a program. Gödel's theorem suggests reality transcends computation. The universe isn't just uncomputably complex, it's fundamentally non-algorithmic. The simulation hypothesis, it turns out, may be mathematically impossible. Our reality is deeper than code. The 2025 paper connects this idea to quantum gravity, where space-time itself isn't fundamental. It emerges from deeper mathematical laws. These laws don't exist within space-time. They generate it, like source code producing a world. But here's the twist. This source code isn't algorithmic. It contains non-computable Gödelian truths. No computer, no matter how powerful, could simulate a universe with infinite, non-repeating complexity. A simulation can only approximate, never fully capture, the richness of our cosmos. It's like trying to write a program that lists every digit of pi. Impossible, because pi is infinite. The very depth that makes the universe seem programmable is evidence it's not. Our universe's laws can't be contained in any algorithm. Reality is richer than any simulation could ever be. The map can never be the territory. We're not living in a video game. We're part of something far more profound. The universe's true nature transcends computation. So, is the Matrix real? The latest evidence says no. While digital metaphors help us understand the universe, they don't prove we're in a simulation. Gödel's theorem suggests our reality is non-computable, deeper than any code. The universe isn't just complex, it's a different kind of thing altogether. This frees us from the fear of being fragile software and invites us to explore a cosmos of limitless depth. Anderson localization and phase transitions remain crucial insights, showing how math shapes reality. But these rules don't imply a programmer. They reveal the universe's own mathematical language. We're not characters in a game, but explorers in a vast evolving cosmos. The laws of physics are clues, not constraints. The universe isn't a simulation to escape, it's a magnificent reality to discover.